Tonight, as you settle into the quiet comfort of your bed and let your mind drift towards sleep, something extraordinary is happening all around you. Beyond your window, past the gentle glow of streetlights and the familiar silhouette of trees, beyond the atmosphere that cradles our planet, an ancient process continues its patient work. The universe itself is growing larger, not in some distant, abstract way, but right now, in this very moment, as you breathe slowly and feel your body relax into rest. This isn't a story from science fiction or a tale spun from imagination. It's one of the most profound discoveries in the history of human understanding, revealed through decades of careful observation and gentle detective work among the stars. Tonight, we'll explore this cosmic mystery together, moving at the pace of your settling thoughts, allowing each idea to unfold naturally as you drift deeper into comfort. The story begins not with dramatic explosions or cosmic violence, but with curiosity. In the early decades of the 20th century, astronomers began to notice something peculiar in the light reaching Earth from distant galaxies. These islands of stars, scattered across the vast ocean of space, seemed to be telling a story that no one had expected to hear. The light itself had been stretched, pulled longer during its journey across the cosmos, shifted toward the red end of the spectrum in a way that suggested movement. Edwin Hubble, working with the massive telescope at Mount Wilson Observatory in California, spent countless quiet nights photographing these distant galaxies. Like a patient gardener tending to delicate flowers, he carefully measured the light from each one, noting how the wavelengths had been stretched during their long journey to Earth. What he discovered was both simple and revolutionary. The farther away a galaxy appeared to be, the more its light had been stretched. This stretching, which astronomers call redshift, painted a picture of a universe in motion. But here's where the story becomes truly remarkable, and where we must pause to let our understanding settle like sediment in still water. The galaxies weren't rushing through space like ships racing across an ocean. Something far more fundamental was happening. Space itself, the very fabric of the cosmos, was expanding. Imagine holding a deflated balloon with dots marked on its surface. As you gently inflate the balloon, the dots don't move across the rubber, yet they grow farther apart as the surface itself stretches. This is what's happening to our universe, but in 3 dimensions instead of 2. This discovery required a complete reimagining of how we think about the cosmos. For centuries, humans had assumed that space was simply an empty stage where cosmic events unfolded. But Einstein's theory of general relativity had already suggested something different. Space and time weren't separate, unchanging backdrops. They were woven together into a single fabric called space-time, and this fabric could bend, stretch, and curve in response to matter and energy. When astronomers realized that the universe was expanding, they were seeing Einstein's equations come to life on the largest possible scale. The expansion wasn't happening at the edges of the universe, pushing outward into some void beyond. There is no beyond, no edge to push against. Instead, every region of space, everywhere throughout the cosmos, is gently stretching, carrying the galaxies along like leaves floating on the surface of a slowly expanding pond. Let's pause here and breathe with this idea for a moment. As you lie comfortable in your bed, the space between distant galaxies is growing larger. In the time it takes for you to complete one slow, peaceful breath, the most distant galaxies observable to our telescopes have moved millions of kilometers farther apart. Not because they're racing through space, but because the space between them has grown. This expansion follows what we now call Hubble's law, named after the astronomer who first measured it. The relationship is elegant in its simplicity. The farther away a galaxy is from us, the faster it appears to be receding. This doesn't mean we're at the center of some cosmic explosion. From any galaxy in the universe, every other galaxy would appear to be moving away following the same pattern. It's a natural consequence of space itself expanding uniformly in all directions. In the 1920s and 1930s, as this picture of an expanding universe emerged, astronomers faced a profound question. If the universe was expanding now, what had it been like in the past? Following the expansion backward through time, like watching a movie in reverse, led to an inescapable conclusion. At some point in the distant past, all the matter and energy in the universe must have been compressed into an incredibly small, incredibly hot state. This moment, roughly 13.8 billion years ago, marked the beginning of everything we can observe. Not an explosion in space, but an explosion of space itself. The Big Bang. From that primordial beginning, the universe has been expanding and cooling, like breath slowly released into cold air. In the first few moments after the Big Bang, the universe underwent a period of incredibly rapid expansion called inflation. Space itself stretched faster than the speed of light, smoothing out irregularities and setting the stage for everything that would follow. As the universe continued to expand and cool, the first atomic nuclei formed in the intense heat. For hundreds of thousands of years, the cosmos remained opaque, filled with a hot fog of charged particles that scattered light in all directions. But eventually, as expansion continued and temperatures dropped, electrons combined with nuclei to form the first neutral atoms. Suddenly, the universe became transparent, and light could travel freely through space. That ancient light, stretched and cooled by billions of years of cosmic expansion, still fills the universe today. We call it the cosmic microwave background radiation, and it provides us with a baby picture of the cosmos when it was only 380,000 years old. This gentle glow, detectable by sensitive radio telescopes, carries the imprint of tiny fluctuations that would eventually grow into galaxies, stars, and all the cosmic structure we see today. For decades after Hubble's discovery, astronomers assumed that the expansion of the universe must be slowing down. After all, gravity pulls everything together, so it seemed natural that the cosmic expansion would gradually decelerate, perhaps even eventually reverse into a cosmic collapse. The question was simply how much the expansion was slowing down. In the 1990s, two teams of astronomers set out to measure this deceleration precisely. They focused on a particular type of exploding star called a Type Ia supernova. These cosmic lighthouses have a remarkable property. They all explode with nearly the same intrinsic brightness, making them perfect standard candles for measuring distances across the cosmos. The astronomers' plan was elegant. By comparing how bright these supernovas appeared to how bright they should appear based on their distance, they could map out the expansion history of the universe with unprecedented precision. They expected to find a universe whose expansion was gradually slowing down under the influence of gravity. What they discovered instead changed our understanding of the cosmos forever. The expansion of the universe wasn't slowing down, it was speeding up. Galaxies weren't just moving apart due to the momentum from the Big Bang. Some unknown force was actively pushing space to expand faster and faster. This discovery was so unexpected, so contrary to every prediction, that both teams checked and rechecked their results for months. But the evidence was undeniable. The universe's expansion was accelerating, and this acceleration had been going on for billions of years. The discovery was so groundbreaking that it earned the 2011 Nobel Prize in Physics. But what could be causing this cosmic acceleration? Astronomers had discovered the effect, but the cause remained completely mysterious. They gave it a name that reflected their ignorance. Dark energy. Not because it was necessarily dark in color, but because it remained hidden from our understanding, as mysterious as the space between the stars. Today, we know that dark energy makes up about 68% of all the matter and energy in the universe. It's everywhere, filling every cubic centimeter of space with a gentle but persistent pressure that pushes space to expand. Unlike matter, which becomes more dilute as space expands. Dark energy maintains a constant density. As the universe grows larger, there's more space, and therefore more dark energy, driving the acceleration ever faster. Think of it this way. As you rest peacefully in your bed tonight, dark energy is working throughout the cosmos like a gentle but inexorable force. In the vast spaces between galaxy clusters, it's pushing space to expand, carrying those distant islands of stars farther and farther apart. The effect is so subtle that it only becomes noticeable over cosmic distances and cosmic timescales. But it never stops, never rests, never takes a break. This leads us to a comforting realization about the scale of cosmic expansion. While the universe grows larger around us, the expansion doesn't affect the space within our solar system, within our planet, or within our bodies. The gravitational bonds that hold Earth in orbit around the Sun, the electromagnetic forces that bind atoms together, the nuclear forces that power the stars, all of these are far stronger than the gentle tug of cosmic expansion on such small scales. You can sleep peacefully knowing that while the universe expands around you, your bedroom remains the same size. The distance between your pillow and the ceiling isn't growing. The space between molecules in your body isn't stretching. The expansion of the universe is a phenomenon of the very largest scales, affecting the distances between galaxy clusters separated by hundreds of millions of light years. Yet on those vast scales, the expansion never stops. Right now, as you settle into sleep, the Andromeda Galaxy, our nearest large galactic neighbor, remains at roughly the same distance because gravity holds our local group of galaxies together. But far beyond our local neighborhood, in the depths of intergalactic space, other galaxy clusters are receding from us and from each other at thousands of kilometers per second. The most distant galaxies that our most powerful telescopes can observe are racing away from us at a significant fraction of the speed of light. In the 8 hours you'll spend sleeping tonight, these distant galaxies will have moved millions of kilometers farther away. Not because they're traveling through space at these incredible speeds, but because the space between us and them will have grown by that amount. This expansion carries profound implications for the future of our cosmos. As dark energy continues to drive acceleration, galaxy clusters will move farther and farther apart. Billions of years from now, the night sky will look very different from any planet that might exist. Distant galaxies will have been carried so far away by expansion that their light will no longer reach us. The observable universe will shrink, not because space itself is getting smaller, but because the sources of light will have been carried beyond our cosmic horizon. But even as we contemplate this far distant future, there's something deeply comforting about the gentle, predictable nature of cosmic expansion. Like the steady rhythm of ocean waves or the reliable turning of seasons, the universe expands according to laws we can understand and measure. This isn't a chaotic or violent process, but something as natural and inevitable as the flow of time itself. The story of how we came to understand this expansion is filled with moments of quiet revelation, each discovery building upon the last like stones carefully placed in a garden path. After astronomers confirmed that the universe was accelerating, they faced an immediate challenge. How could they study this mysterious dark energy in more detail? How could they trace its effects back through cosmic history? The answer came through increasingly sophisticated observations of those same Type Ia supernovas that had revealed acceleration in the first place. But now, instead of studying dozens of these stellar explosions, astronomers began cataloguing thousands of them. Each supernova served as a lighthouse, its light carrying information about the expansion of space during its journey to Earth. The Dark Energy Survey, a massive international collaboration, spent 6 years systematically photographing a portion of the southern sky. Using a camera containing 570 million pixels, roughly 100 times more sensitive than a typical smartphone camera, they captured images of galaxies billions of light years away. Hidden within this cosmic census were several thousand supernovas, each one a data point in the grand story of universal expansion. What emerged from this painstaking work was a detailed map of how dark energy has behaved over the past several billion years. The results painted a picture of remarkable consistency. Throughout cosmic history, dark energy appears to have maintained an almost perfectly constant density, neither strengthening nor weakening as the universe expanded around it. This consistency is itself deeply mysterious. Most forms of energy become diluted as space expands. If you have a certain amount of gas in a container and you make the container larger, the gas spreads out and becomes less dense. But dark energy seems to maintain the same density even as the universe grows. It's as if the universe creates new dark energy to fill the new space created by expansion, maintaining a perfectly constant pressure that drives continued acceleration. Yet even as this picture of constant dark energy emerged from supernova studies, other observations began to hint at subtle complexities. The Dark Energy Spectroscopic Instrument, known as DESI, represents one of the most ambitious attempts to map the universe's expansion history with unprecedented precision. This remarkable instrument can measure the distances to millions of galaxies simultaneously, creating a three-dimensional map of cosmic structure spanning most of the universe's history. DESI works by detecting incredibly faint patterns in the way galaxies cluster together across space. These patterns, called baryon acoustic oscillations, are like fossilized sound waves from the early universe. In the first few 100,000 years after the Big Bang, when the cosmos was still hot enough that matter and radiation were intimately connected, sound waves rippled through the primordial plasma, like waves across the surface of a cosmic ocean. When the universe cooled enough for the first atoms to form, these sound waves became frozen into the distribution of matter, creating a characteristic scale that we can still observe today in how galaxies are arranged. As the universe has expanded over billions of years, this characteristic scale has been stretched along with space itself. By measuring how much it has been stretched, astronomers can determine how much the universe has expanded since those early times. The preliminary results from DESI have been both reassuring and puzzling. They confirm the overall picture of an accelerating universe driven by dark energy, but they also hint that dark energy might not be quite as perfectly constant as earlier measurements suggested. The data seems to show subtle variations in dark energy's behavior over cosmic time, as if this mysterious force has been slowly evolving as the universe ages. These observations are still being carefully analyzed and debated as scientists work to understand whether they represent real changes in dark energy or simply reflect the limitations of our measurement techniques. But they remind us that our understanding of cosmic expansion continues to deepen and evolve, like a photograph slowly coming into focus in a dark room. As you rest tonight, it's worth reflecting on the extraordinary fact that we can study the expansion of the universe at all. The light that reaches our telescopes tonight began its journey billions of years ago, when the universe was younger and smaller. By collecting and analysing this ancient light, we're literally looking back in time, watching the universe evolve and expand over cosmic ages. The most distant galaxies we can observe appear to us as they were when the universe was less than 1 billion years old. Their light has been travelling toward us for more than 13 billion years, stretched and redshifted by the expansion of space during that enormous journey. When astronomers photograph these distant galaxies, they're seeing cosmic history unfold, watching the universe grow and change over timescales that dwarf human experience. This cosmic perspective can be both humbling and oddly comforting. The universe operates on scales of space and time that make our daily concerns seem small, yet the same physical laws that govern cosmic expansion also operate here on Earth. The gravity that holds you gently against your mattress tonight is the same force that shapes the large-scale structure of the universe. The electromagnetic forces that power the neurons in your brain are cousins to the forces that make stars shine and galaxies glow. Even the atoms in your body tell the story of cosmic expansion. The hydrogen in the water that makes up most of your cells was forged in the first few minutes after the Big Bang, when the universe was hot enough for nuclear reactions to occur. The heavier elements, the carbon in your DNA, the oxygen you breathe, the calcium in your bones, were created much later in the nuclear furnaces of massive stars. These stars lived their lives, burned their nuclear fuel, and eventually exploded as supernovas, scattering their newly created elements into space. Over billions of years, as the universe continued to expand and cool, these elements came together in new clouds of gas and dust, eventually condensing to form new stars, new planets, and eventually, new life. In a very real sense, you are made of ancient starlight, of elements forged in cosmic furnaces and scattered across space by stellar explosions. The expansion of the universe has carried these building blocks of life across vast distances, mixing and stirring the cosmic soup from which everything we know has emerged. This connection between cosmic expansion and the existence of life itself reveals another comforting aspect of our expanding universe. The expansion has been proceeding at just the right rate to allow complexity to emerge. If the universe had expanded too quickly after the Big Bang, matter would have been spread so thin that stars and galaxies could never have formed. If it had expanded too slowly, everything would have collapsed back together before life could evolve. Instead, cosmic expansion has proceeded at a rate that allowed gravity to pull matter together into stars and galaxies, while still providing the time and space needed for complex structures to develop. The delicate balance between expansion and gravitational attraction has created a universe where islands of complexity can emerge and flourish amid the vast ocean of expanding space. As you settle deeper into sleep tonight, you might find it peaceful to imagine yourself as part of this grand cosmic story. Your body rests on a planet orbiting a star in a galaxy that is itself part of a vast cosmic web of structure, all of it embedded in the gently expanding fabric of space-time. The same physical processes that created the atoms in your body are still operating throughout the universe, in stellar cores millions of times hotter than the surface of the sun. The expansion of space continues its patient work, carrying distant galaxies farther apart while leaving the local structure of our cosmic neighborhood essentially unchanged. The Milky Way galaxy, our cosmic home, contains hundreds of billions of stars, many likely accompanied by planets of their own. Gravity holds this entire magnificent spiral structure together, keeping it intact even as the universe expands around it. Our neighboring galaxy, Andromeda, lies about 2.5 million light-years away, approaching us through space at roughly 100 kilometers per second. In about 4.5 billion years, these two galaxies will merge, creating a larger elliptical galaxy that astronomers have already nicknamed Milkomeda. Even this cosmic collision will be a gentle process, playing out over hundreds of millions of years as gravity slowly reshapes both galaxies. This merger will occur against the backdrop of continued cosmic expansion. By the time our galaxy merges with Andromeda, most of the other galaxy clusters visible in today's sky will have been carried much farther away by the expansion of space. The universe will be larger, older, and in some ways, lonelier, with vast gulfs of expanding space separating the remaining islands of matter. Yet even in that distant future, the fundamental processes that make life possible will continue. Stars will still form from collapsing clouds of gas and dust. Planets will still condense from the debris disks around young stars. And somewhere, in ways we cannot yet imagine, new forms of complexity and perhaps even new forms of consciousness may emerge. The expansion of the universe ensures that there will always be room for new possibilities, new structures, new forms of beauty, to emerge from the quantum fluctuations that populate the vacuum of space. Dark energy, whatever its ultimate nature, provides a kind of cosmic canvas that continues to grow, offering infinite space for the universe to explore its own creative potential. Recent observations have begun to reveal even more subtle aspects of how cosmic expansion affects the structure of the universe. Scientists studying the cosmic microwave background radiation, that ancient afterglow of the Big Bang, have detected incredibly tiny variations in temperature across the sky. These variations, just a few millionths of a degree, represent the seeds from which all cosmic structure has grown. As the universe expanded and cooled, regions that were slightly denser than average began to attract more matter through gravity, while regions that were slightly less dense became increasingly empty. Over millions and billions of years, this process created the cosmic web we observe today, with galaxies strung along vast filaments of dark matter, separated by enormous voids where very little matter exists. The expansion of space has played a crucial role in shaping this cosmic architecture. Without expansion, gravity would have caused all matter to collapse together into a single massive black hole shortly after the Big Bang. With too rapid expansion, matter would have been spread so thin that no structures could have formed at all. The actual rate of expansion has been just right to allow the delicate dance between gravity and expansion that has created the rich tapestry of cosmic structure we see today. These cosmic voids, the largest structures in the universe, are truly vast beyond easy comprehension. Some are hundreds of millions of light years across, containing very little matter except for the occasional lonely galaxy drifting through the darkness. As cosmic expansion continues, these voids grow ever larger and emptier, stretching the space between the rare galaxies they contain. Yet even in these seemingly empty regions, space itself is far from truly empty. Quantum mechanics tells us that even the vacuum of space is alive with virtual particles constantly appearing and disappearing, borrowing energy from the vacuum for brief moments before annihilating each other and returning that energy to the quantum field. Dark energy itself may be related to this quantum activity, though the connection remains one of the deepest mysteries in modern physics. The relationship between cosmic expansion and the quantum nature of reality opens up profound questions about the ultimate fate of the universe. As expansion continues and accelerates, will the quantum vacuum remain stable, or might it undergo transitions that fundamentally change the nature of space and time? These questions push at the very boundaries of our current understanding, reminding us how much mystery still surrounds the cosmos we inhabit. For now, as you drift towards sleep, you can rest assured that the expansion of the universe proceeds according to well-understood physical laws. The same equations that describe the fall of an apple from a tree also govern the expansion of space on the largest scales. The universe may be vast and mysterious, but it operates according to principles we can study, measure, and gradually understand. Tomorrow morning, when you wake, the universe will be measurably larger than it was when you went to sleep. The most distant galaxies will have receded by millions of kilometers. New photons of cosmic microwave background radiation will be reaching Earth for the first time after traveling for nearly 14 billion years. And throughout the cosmos, the patient work of cosmic evolution will continue, as gravity and expansion together shape the future of everything we can see. In this gentle, ongoing process of cosmic growth, there is something profoundly peaceful. The universe expands not through violence or chaos, but through the steady, predictable operation of natural law. Like the growth of a tree or the changing of the seasons, cosmic expansion follows rhythms deeper than human time, connecting us to processes that began before the Earth existed and will continue long after the last star has burned out. As you surrender to sleep tonight, let yourself be carried by this cosmic rhythm, this ancient dance between matter and space, gravity and expansion that has been unfolding since the beginning of time. In the morning, you'll wake to a universe that is slightly larger, slightly older, and filled with the same gentle forces that have been shaping the cosmos since the very first moment of creation. First moment of creation. Even the most sophisticated measurements of cosmic expansion reveal something remarkable about the nature of scientific discovery itself. Each new observation, each refinement in our instruments brings us closer to understanding forces that operate on scales almost beyond imagination. Yet the more we learn, the more we realize how much mystery still surrounds us, like explorers mapping the coastline of an infinite ocean. In recent years, astronomers have developed increasingly elegant ways to study the expansion of space. One of the most beautiful involves listening to echoes from the very early universe. These echoes aren't sounds in any conventional sense, but rather patterns in how matter is distributed throughout the cosmos. Frozen remnants of acoustic waves that once rippled through the hot, dense plasma that filled the universe in its first few 100,000 years. Imagine the early universe as a vast ocean of particles and energy, so hot that atoms couldn't yet form. In this primordial soup, pressure waves traveled back and forth like sound waves in water, creating regions of slightly higher and lower density. When the universe finally cooled enough for atoms to form and light to travel freely, these waves became frozen in time, preserved in the pattern of how matter was spread throughout space. Today, billions of years later, we can still see the effects of those ancient sound waves in how galaxies cluster together. There's a characteristic scale, a preferred distance at which galaxies tend to group that reflects the size of those primordial pressure waves. But here's what makes this observation so profound for understanding cosmic expansion. That characteristic scale has been stretched by the expansion of space itself. By measuring how much this ancient ruler has been stretched, astronomers can determine precisely how much the universe has expanded since those early times. It's like finding an old photograph with known dimensions and using it to measure how much a room has grown. The technique is so precise that scientists can map the expansion history of the universe with extraordinary accuracy, tracing how the rate of expansion has changed over cosmic time. These measurements have revealed something unexpected about the behavior of dark energy. While earlier observations suggested that this mysterious force had remained perfectly constant throughout cosmic history, newer data hints at subtle changes. Dark energy might be slowly evolving, its strength or character shifting in ways so gradual that they only become apparent when viewed across billions of years. This possibility has profound implications for our understanding of the cosmos. If dark energy is truly constant, as many theories suggest, then the future of the universe follows a relatively predictable path. Expansion will continue to accelerate, eventually carrying distant galaxies beyond our ability to observe them. The cosmos will grow larger, cooler, and increasingly empty as matter spreads ever more thinly through expanding space. But if dark energy is changing, even slowly, then the future becomes much more uncertain. The force that currently drives acceleration might eventually weaken, allowing gravity to slow the expansion once again. Or it might strengthen, leading to ever more rapid acceleration that could eventually overcome even the strong nuclear forces that hold atomic nuclei together. These questions push at the very frontiers of our knowledge, reminding us that the universe still holds secrets we're only beginning to glimpse. Yet there's something deeply comforting about the methodical way scientists approach these mysteries. Each observation is carefully checked and rechecked. Every measurement is compared with others using different techniques. Slowly, patiently, our picture of cosmic expansion grows more complete and more precise. The instruments used to study expansion have themselves become marvels of human ingenuity. The dark energy camera, mounted on a telescope high in the Chilean Andes, contains sensors so sensitive they could detect the light from a single candle on the moon. Over 6 years of observations, it photographed an area of sky nearly 1/8 the size of the entire celestial sphere, cataloguing the light from hundreds of millions of galaxies. Hidden within this cosmic census were thousands of supernovas, each one a stellar explosion so bright it could briefly outshine an entire galaxy of 100 billion stars. By measuring the precise brightness and color of light from these distant explosions, astronomers could determine how far away they were and how fast space was expanding when their light began its long journey to Earth. Each supernova serves as a time capsule, carrying information about the state of the universe when it exploded. Those that detonated recently tell us about the current rate of expansion. Others, whose light has been traveling for billions of years, reveal how far space was expanding in the distant past. By comparing supernovas of different ages, scientists can trace the complete history of cosmic expansion from the early universe to the present day. This archaeological approach to studying the cosmos reveals expansion as a process that has unfolded gradually over cosmic time. In the earliest epochs after the Big Bang, when the universe was much denser than today, gravity dominated over dark energy. The expansion was actually slowing down, decelerated by the gravitational attraction between all the matter in the universe. But as expansion continued and matter became more spread out, its gravitational influence weakened. Dark energy, which maintains a constant density even as space grows, gradually became the dominant force. About 5 billion years ago, around the time our solar system was forming, dark energy overtook matter and began to accelerate the expansion. This transition marks one of the great turning points in cosmic history. Before this moment, the universe was slowing down, its expansion gradually decelerating under the influence of gravity. After this point, dark energy took control and expansion began to accelerate. We live in this age of acceleration, watching the cosmos grow faster and faster as time passes. The timing of this transition isn't coincidental. It occurred roughly when the universe had expanded enough that matter had become sufficiently dilute for dark energy to take over. This suggests a deep connection between the amount of matter in the universe, the strength of dark energy, and the overall evolution of the cosmos. Scientists are still working to understand these connections and what they might tell us about the fundamental nature of reality. As you rest tonight, this cosmic transition continues to unfold around you. Dark energy maintains its gentle but persistent pressure throughout every cubic centimeter of space, pushing the universe to expand ever faster. The effect is so subtle on human scales that you cannot feel it, but on the vast distances between galaxy clusters, it drives motion at speeds of thousands of kilometers per second. The most distant galaxies visible to our most powerful telescopes are receding from us at more than 90% the speed of light, not because they're moving through space at these incredible velocities, but because the space between us and them is expanding so rapidly. In the time you'll spend sleeping tonight, these distant galaxies will have been carried millions of kilometers farther away by the expansion of space itself. Yet this process, dramatic as it sounds, unfolds with a gentleness that matches the rhythm of your breathing. Cosmic expansion doesn't happen in sudden jerks or violent motions. It proceeds smoothly and continuously, like the slow growth of a tree or the gradual change of seasons. The universe grows larger in the same patient way that mountains rise or canyons deepen, through the accumulated effect of countless small changes over enormous spans of time. This steady, predictable nature of expansion reflects the deep mathematical structure that underlies all cosmic evolution. Einstein's equations, which describe how matter and energy curve space-time, predict not just that the universe should expand, but exactly how that expansion should proceed under different conditions. The observations match these predictions with remarkable precision, confirming our understanding of how gravity and dark energy work together to shape the cosmos. The equations also reveal something beautiful about the relationship between local and cosmic scales. While dark energy drives expansion on the larger scales, it has virtually no effect on smaller structures like galaxies, solar systems, or planets. The gravitational forces that hold these structures together are far stronger than the gentle tug of cosmic expansion. This means that as the universe expands around us, the space within our galaxy remains essentially unchanged. The distance between stars in our cosmic neighborhood doesn't grow. The orbits of planets around their suns stay stable. The atoms in your body maintain their same size and structure. Cosmic expansion affects only the vast gulfs of space between galaxy clusters, leaving the architecture of smaller structures intact. This separation of scales provides a kind of cosmic protection for complexity and life. Galaxies can continue to form stars, planets can maintain stable orbits, and biological evolution can proceed, all while the universe grows larger around them. It's as if the cosmos has organized itself into a hierarchy of structures, each scale governed by different forces, allowing complexity to flourish even in an expanding universe. The future that cosmic expansion promises is one of gradual change rather than dramatic catastrophe. As dark energy continues to drive acceleration, the night sky will slowly evolve over billions of years. Distant galaxies will fade from view as their light becomes too redshifted to detect. The cosmic microwave background radiation will grow cooler and dimmer as its photons are stretched to longer and longer wavelengths. But this future unfolds over timescales so vast that they dwarf the entire history of life on Earth. The Sun will complete its entire life cycle, from its current middle age through its eventual transformation into a white dwarf star, long before cosmic expansion has any noticeable effect on our local cosmic environment. Countless generations of stars will be born, live their lives, and die before the expansion of space significantly changes the appearance of our galaxy. This vast temporal perspective offers a profound sense of cosmic patience. The universe operates according to rhythms that extend far beyond human experience, yet the same physical laws that govern these cosmic processes also operate here and now. The electromagnetic forces that power your nervous system are identical to those that make stars shine. The gravity that holds you gently against your bed is the same force that shapes the large-scale structure of the universe. Even the quantum mechanical principles that govern the behavior of individual atoms play a role in cosmic expansion. The vacuum of space itself, far from being truly empty, seethes with quantum activity. Virtual particles constantly appear and disappear, borrowing energy from the quantum field for brief moments before returning it. Some theories suggest that this quantum activity might be related to dark energy, though the connection remains one of the deepest puzzles in physics. The relationship between the quantum world and cosmic expansion reveals how the very small and the very large are intimately connected in ways we're only beginning to understand. The same uncertainty principle that prevents us from knowing both the position and momentum of an electron with perfect precision may also play a role in the energy that drives the acceleration of space itself. These connections remind us that the universe is not a collection of separate, unrelated phenomena, but rather a single, integrated system where every part influences every other part. The expansion of space affects the evolution of galaxies, which influences the formation of stars, which determines the creation of heavy elements, which makes possible the chemistry of life. Everything is connected in an intricate web of cause and effect that stretches from the quantum scale to the cosmic scale. As you drift deeper into sleep, you can take comfort in this cosmic interconnectedness. You are not separate from the universe around you, but rather an integral part of its ongoing evolution. The atoms in your body were forged in stellar cores billions of years ago. The oxygen you breathe was created in the nuclear fusion reactions that power massive stars. The carbon that forms the backbone of every molecule in your cells was scattered into space by ancient supernovas. The expansion of the universe has played a crucial role in your existence. Without cosmic expansion, the universe would have collapsed back on itself, long before stars could form and create the heavy elements necessary for life. The precise balance between expansion and gravitational attraction has created a cosmos where complexity can emerge and flourish over billions of years. This balance continues to shape the universe today. As you sleep, new stars are forming in galaxies billions of light years away. Planets are condensing from disks of gas and dust around young suns. And somewhere in the vast cosmos, the chemical elements created in stellar cores are coming together in new combinations that might someday give rise to new forms of life and consciousness. The expansion of space ensures that there will always be room for these new possibilities to unfold. Dark energy provides a kind of cosmic canvas that continues to grow, offering infinite space for the universe to explore its own creative potential. Each cubic meter of space that comes into existence through expansion represents new territory for matter and energy to organize themselves in novel ways. Recent observations have begun to reveal even more subtle aspects of this cosmic creativity. Scientists studying the formation of the first galaxies have discovered that these early stellar systems were quite different from the galaxies we see today. They were smaller, more chaotic, and burned through their stellar fuel much more rapidly. Over billions of years of cosmic evolution, as space continued to expand and cool, galaxies gradually became larger, more organized, and more efficient at forming long-lived stars. This galactic evolution continues today, driven by the same expansion that carries distant galaxies away from us. As space grows larger, it provides more room for gravity to collect matter into ever more massive structures. Galaxy clusters continue to grow by capturing smaller groups of galaxies. Individual galaxies merge and evolve, creating new stellar populations and triggering fresh bursts of star formation. The Milky Way itself participates in this ongoing cosmic dance. Our galaxy is slowly approaching Andromeda, our nearest large neighbor, drawn together by gravity despite the overall expansion of space. In about 4.5 billion years, these two spiral galaxies will merge, creating a new, larger elliptical galaxy that astronomers have playfully nicknamed Milkomeda. This future collision will be a gentle process, unfolding over hundreds of millions of years as gravity gradually reshapes both galaxies. Individual stars will rarely collide, since the distances between them are so vast compared to their sizes. Instead, stellar orbits will be stirred and rearranged as the two galactic gravitational fields interact and eventually merge. Even this dramatic cosmic event will occur against the backdrop of continued universal expansion. By the time our galaxy merges with Andromeda, most other galaxy clusters will have been carried much farther away by the expansion of space. The universe will be larger, older, and in some ways lonelier, with vast gulfs of expanding space separating the remaining islands of matter and light. Yet even in that distant future, the fundamental processes that make complexity possible will continue to operate. Stars will still condense from clouds of gas and dust, planets will still form from the debris around young suns, and the expansion of space will continue to provide room for new structures and new possibilities to emerge from the quantum fluctuations that populate even the emptiest regions of space. The story of cosmic expansion is ultimately a story about time itself and how it shapes everything we observe. The universe has a history, a past that we can study by looking at distant galaxies whose light has been traveling toward us for billions of years. It has a present, which we observe in the current rate of expansion and the ongoing formation of new stars and galaxies. And it has a future, which we can predict based on our understanding of the forces that drive cosmic evolution. This temporal dimension of the cosmos provides a profound perspective on your own existence. You are part of a story that began 13.8 billion years ago with the Big Bang and continues to unfold today through the expansion of space. The same physical processes that shaped the early universe continue to operate around you, creating new stars, new planets, and new opportunities for complexity to emerge. Your life unfolds within this cosmic context, connected to processes that operate on scales of space and time far beyond direct human experience. Yet those connections are real and profound. The expansion of the universe has created the conditions necessary for your existence, and it continues to shape the cosmic environment in which life and consciousness can flourish. As you settle into deeper rest tonight, you can feel yourself as part of this grand cosmic story. Your breathing slows and deepens, matching the patient rhythm of cosmic evolution. Your heartbeat echoes the steady pulse of stellar nucleosynthesis, the fusion reactions that create new elements in the cores of massive stars. Your thoughts drift like galaxies carried apart by the gentle expansion of space, each one connected to the others by invisible threads of causation and meaning. The expansion of the universe proceeds around you with the same quiet inevitability as your own descent into sleep. Both processes unfold according to natural laws, following patterns deeper than conscious will or intention. Just as your body knows how to rest and restore itself without conscious effort, the cosmos knows how to grow and evolve according to the fundamental principles encoded in the structure of space-time itself. In this cosmic rhythm, there is something deeply peaceful and reassuring. The universe expands not through struggle or conflict, but through the natural expression of its own deepest nature. Dark energy doesn't fight against gravity. Rather, both forces work together to create the complex dance of expansion and structure formation that has shaped cosmic history from the beginning. This cooperation between opposing forces mirrors the balance in your own life between activity and rest, tension and relaxation, growth and stability. Just as the universe finds harmony between the outward push of dark energy and the inward pull of gravity, you find balance between the demands of waking life and the restorative power of sleep. Tomorrow morning, when consciousness returns and you open your eyes to a new day, the universe will be measurably larger than when you closed them tonight. Somewhere in the vast cosmos, light that has been traveling since before the Earth formed will reach our telescopes for the first time. New stars will have ignited in distant galaxies. Planets will have completed another fraction of their orbits around their parent suns. And throughout all of this cosmic activity, the expansion of space will continue its patient work, carrying the most distant galaxies farther apart, while leaving the local structure of matter essentially unchanged. The same forces that shaped the universe in its earliest moments will still be operating, creating new possibilities for complexity and consciousness to emerge from the quantum foam that underlies all of reality. In the morning, you'll wake refreshed and renewed, ready to participate once again in the ongoing story of cosmic evolution. Your thoughts and actions, however small they may seem against the backdrop of an expanding universe, are part of the same creative process that builds galaxies and gives birth to stars. You are both observer and participant in the grandest story ever told, the tale of how space and time and matter and energy have organized themselves into the magnificent cosmos we call home. But for now, as the night deepens around you and your breathing becomes slower and more regular, you can rest in the knowledge that the universe continues its ancient dance of expansion and evolution. Dark energy maintains its gentle pressure throughout every corner of space. Galaxies drift apart like islands in an ever-expanding ocean, and somewhere in the vast cosmos, new forms of beauty and complexity are emerging from the marriage of natural law and cosmic time. Sleep peacefully in this expanding universe, knowing that its growth makes space for infinite possibilities, infinite forms of wonder, infinite opportunities for consciousness to awaken and contemplate its own cosmic origins. The universe expands while you sleep, and in that expansion lies the promise of tomorrow and all the tomorrows yet to come, stretching out into a future as vast and full of potential as the cosmos itself. As the cosmos itself. The nature of this cosmic expansion reveals itself through the most subtle of observations, each one building upon the last like layers of sediment settling in the depths of a quiet lake. Scientists have learned to read the universe's history written in wavelengths of light, in the gentle stretching of electromagnetic radiation as it journeys across billions of years to reach our waiting telescopes. When astronomers first began to understand what they were seeing, they realized that every photon of light carries within it a story of the space it has traveled through. As these particles of light move through expanding space, the space itself grows larger during their journey, stretching the wavelengths like notes played on an ever-lengthening string. This stretching shifts the light toward the red end of the spectrum, creating what scientists call cosmological redshift. The beauty of this process lies in its mathematical elegance. The amount by which light is redshifted tells us precisely how much the universe has expanded since that light began its journey. A galaxy whose light is redshifted by 10% reveals that space has grown 10% larger since the photons left that distant star system. It's as if each ray of light carries a timestamp, marking the size of the universe when its journey began. This relationship between redshift and cosmic expansion has allowed astronomers to create what is essentially a motion picture of the universe's growth, played out across billions of years. By observing galaxies at different distances, and therefore different ages, scientists can watch the expansion rate change over cosmic time. Nearby galaxies show us how fast space is expanding today. More distant ones reveal the expansion rate millions or billions of years ago. What emerges from these observations is a story of cosmic evolution that unfolds with the patience of geological time. In the universe's youth, when matter was much denser than it is today, gravity exerted a stronger influence on the expansion rate. The universe was growing, yes, but its growth was gradually slowing down as gravity worked to pull everything back together. This deceleration continued for billions of years, like a ball thrown upward, gradually losing speed as gravity pulls it back down. Astronomers expected to find evidence of this cosmic slowdown when they began their careful measurements of distant supernovas in the 1990s. What they discovered instead would fundamentally change our understanding of the universe's fate. The measurements revealed that the cosmic expansion had not been slowing down as expected. Instead, sometime around 5 billion years ago, the expansion began to speed up. The universe entered a new phase of its evolution, one dominated not by the inward pull of gravity, but by the outward push of something entirely mysterious and unexpected. This mysterious force, which scientists have named dark energy, appears to be woven into the very fabric of space itself. Unlike matter, which becomes more dilute as the universe expands, dark energy maintains a constant density throughout all of space. As the universe grows larger, creating more volume, there is proportionally more dark energy, and therefore more pressure driving the acceleration. The implications of this discovery ripple through every aspect of cosmology. Dark energy currently makes up about 68% of all the energy in the universe, making it the dominant component of cosmic evolution. Yet despite its overwhelming importance, dark energy remains profoundly mysterious. Scientists know it exists because they can measure its effects, but its fundamental nature continues to elude our understanding. Current theories suggest that dark energy might be a property of space itself, a kind of inherent pressure that emerges from the quantum mechanical nature of the vacuum. At the smallest scales, even empty space is alive with quantum fluctuations, virtual particles that briefly appear and disappear in a constant dance of creation and annihilation. Some physicists speculate that these quantum processes might give rise to the dark energy that drives cosmic acceleration. However, when scientists calculate how much dark energy should arise from quantum fluctuations, they get a number that is enormously larger than what observations actually measure. This discrepancy, sometimes called the worst prediction in the history of physics, highlights how much we still don't understand about the fundamental nature of space, time, and energy. Other theories propose that dark energy might be a new kind of field that permeates all of space, similar to the electromagnetic field but with very different properties. This hypothetical field, sometimes called quintessence, might change its strength over cosmic time. leading to variations in the expansion rate that future observations might be able to detect. Still, other ideas suggest that our understanding of gravity itself might be incomplete. Perhaps Einstein's theory of general relativity, while extraordinarily successful at describing gravity on smaller scales, needs modification when applied to the vast distances and long time scales of cosmic evolution. These alternative theories of gravity might explain the apparent acceleration without requiring a mysterious dark energy at all. The truth is that scientists simply don't yet know which, if any, of these explanations is correct. This uncertainty doesn't represent a failure of science, but rather the exciting frontier where human knowledge meets the unknown. Each new observation, each refined measurement, brings us closer to understanding one of the deepest mysteries in the universe. As you rest tonight, this mystery continues to unfold around you. Dark energy, whatever its true nature, maintains its influence throughout every cubic centimeter of space. From the vast voids between galaxy clusters to the space between molecules in your body. Yet its effects are so subtle on small scales that you cannot feel its presence, even though it surrounds and permeates everything you know. The expansion driven by dark energy operates according to a principle that might seem counterintuitive at first. The farther apart two objects are in space, the faster they appear to be moving away from each other. This relationship, known as Hubble's law after the astronomer who first measured it, means that the most distant galaxies observable to our telescopes are receding from us at tremendous speeds. Galaxies located billions of light years away are moving away from us at velocities that approach a significant fraction of the speed of light itself. In the 8 hours you spend sleeping tonight, these most distant galaxies will have been carried millions of kilometers farther away by the expansion of space. Not because they are racing through space at these incredible speeds, but because the space between us and them continues to grow. This distinction between motion through space and the expansion of space itself is crucial to understanding cosmic expansion. Galaxies aren't flying apart like debris from an explosion. Instead, they are being carried apart by the growth of the space that contains them, like raisins in a loaf of bread dough that expands as it rises. The expansion affects different scales in dramatically different ways. On the largest scales, where dark energy dominates over gravity, space expands freely, and galaxy clusters move apart. On smaller scales, where gravity is stronger, structures remain bound together despite the overall expansion of the universe. Our own galaxy, the Milky Way, is gravitationally bound to our neighbour Andromeda and several smaller galaxies in what astronomers call the local group. Even though the universe is expanding all around us, the gravitational attraction between these nearby galaxies is strong enough to hold our local cluster together. In fact, Andromeda is actually approaching us, drawn by gravity across the 2.5 million light years that currently separate our galaxies. On even smaller scales, the expansion has essentially no effect at all. Our solar system maintains its structure as the planets continue their stable orbits around the Sun. The Earth remains the same size, held together by gravitational and electromagnetic forces that are vastly stronger than the gentle tug of cosmic expansion. The atoms in your body retain their normal sizes and properties, unaffected by the growth of space on cosmic scales. This hierarchy of scales provides a natural protection for complexity and life. While the universe expands on the largest scales, creating ever more space for new possibilities to emerge, the smaller structures that make life possible remain stable and intact. Stars continue to shine, planets maintain their orbits, and biological processes proceed normally, all while embedded in an expanding cosmos. The measurements that reveal this cosmic expansion require extraordinary precision and ingenuity. Astronomers have developed increasingly sophisticated techniques to measure distances across the universe, each method carefully calibrated against others to ensure accuracy. The cosmic distance ladder, as scientists call it, uses nearby objects of known brightness to calibrate more distant ones. building a chain of measurements that extends to the very edge of the observable universe. Type Ia supernovas serve as crucial rungs in this distance ladder. These stellar explosions occur when a white dwarf star accumulates matter from a companion until it reaches a critical mass and detonates in a thermonuclear explosion. Because this critical mass is always the same, these supernovas always explode with nearly identical intrinsic brightness, making them perfect standard candles for measuring cosmic distances. When astronomers observe a Type Ia supernova in a distant galaxy, they can determine how far away it is by comparing its apparent brightness to its known intrinsic brightness. The dimmer it appears, the farther away it must be. By combining this distance measurement with observations of the galaxy's redshift, scientists can determine how far space was expanding when that supernova exploded. The Hubble Space Telescope has been instrumental in these measurements, providing the clear, stable observations needed to detect and study supernovas in galaxies billions of light-years away. From its vantage point above Earth's atmosphere, Hubble can measure tiny variations in brightness and color that would be impossible to detect from the ground. More recently, the James Webb Space Telescope has begun to extend these measurements even farther into the cosmos. With its large mirror and sensitive infrared detectors, Webb can observe galaxies so distant that their light has been traveling toward us for more than 13 billion years, showing us the universe as it appeared when it was less than 1 billion years old. These observations reveal that the expansion rate hasn't been constant throughout cosmic history. In the early universe, when matter was much denser, gravity dominated and the expansion was actually slowing down. Only later, as space expanded and matter became more dilute, did dark energy begin to take control and drive acceleration. The transition from decelerated to accelerated expansion marks one of the most significant events in cosmic history. It occurred approximately 5 billion years ago, around the time our solar system was forming from a cloud of gas and dust in the outer regions of the Milky Way galaxy. Before this transition, the universe was dominated by matter and radiation. After it, dark energy took control of cosmic evolution. This timing isn't coincidental. It reflects the changing balance between matter and dark energy as the universe expanded and evolved. In the dense early universe, matter dominated because its gravitational effects were much stronger than the influence of dark energy. But as expansion continued and matter became more spread out, its gravitational influence weakened while dark energy maintained its constant density and pressure. Understanding this cosmic transition helps scientists predict the future evolution of the universe. As expansion continues and accelerates, matter will become even more dilute, making dark energy ever more dominant. The expansion rate will continue to increase, eventually carrying distant galaxies beyond our ability to observe them. This future unfolds over timescales that dwarf all of human history. Billions of years from now, the night sky will look very different from any planet that might exist. Most of the galaxies currently visible will have been carried so far away by expansion that their light will no longer reach us. The observable universe will appear to shrink, not because space is getting smaller, but because the sources of light will have receded beyond our cosmic horizon. Yet even this distant future holds possibilities for complexity and life. Stars will continue to form from clouds of gas and dust, though at a much slower rate than today, as the raw materials become more spread out. Planets will continue to orbit these new stars, and the chemical elements necessary for life will still exist, created in the nuclear furnaces of massive stars and scattered by supernovas into space. The expansion of the universe ensures that there will always be room for new structures to emerge. As space grows larger, it provides an ever-expanding canvas for matter and energy to organize themselves in novel ways. The same quantum fluctuations that may drive dark energy also ensure that even the emptiest regions of space contain the seeds for future structure formation. Recent observations have begun to reveal subtle complexities in how dark energy behaves over cosmic time. The Dark Energy Spectroscopic Instrument, or DESI, has created the most detailed map of cosmic structure ever attempted, measuring the distances to millions of galaxies with unprecedented precision. The preliminary results suggest that dark energy might not be perfectly constant, but may instead evolve slowly as the universe ages. These hints of changing dark energy represent one of the most exciting frontiers in modern cosmology. If confirmed by future observations, they would require a fundamental revision in our understanding of what drives cosmic acceleration. The implications could extend to the most basic questions about the nature of space, time, and energy. However, scientists remain cautious about these early results. The measurements are at the very edge of current observational capabilities, and it will take years of additional data collection and analysis to determine whether the hints of evolving dark energy are real or simply reflect the limitations of our instruments and techniques. This careful, methodical approach to understanding cosmic expansion reflects the broader nature of scientific discovery. Each observation builds upon previous ones. Each measurement is checked and rechecked using different methods, and each new finding is scrutinized by the global community of scientists before being accepted as reliable knowledge. The tools used to study cosmic expansion have themselves become marvels of human engineering and ingenuity. The cameras and spectrographs that detect light from distant galaxies are so sensitive they could measure the light from a single candle placed on the moon. The mirrors of space telescopes are polished to such precision that their surfaces deviate from perfect smoothness by less than the thickness of a soap bubble. These instruments allow astronomers to peer deeper into space and therefore farther back in time than ever before. Light from the most distant galaxies has been traveling toward us for so long that it shows us the universe as it existed when it was just a small fraction of its current age. By studying galaxies at different distances, scientists can watch cosmic expansion unfold across billions of years of history. The cosmic microwave background radiation provides another window into the expansion history of the universe. This faint glow, detectable in every direction we look, is the cooled remnant of the hot radiation that filled the universe when it was only 380,000 years old. The tiny temperature variations in this ancient light carry information about the density fluctuations that would eventually grow into galaxies and galaxy clusters. As space has expanded over the past 13.8 billion years, this primordial radiation has been stretched along with it. What began as visible light has been redshifted all the way into the microwave portion of the electromagnetic spectrum, cooling from thousands of degrees to just 2.7 degrees above absolute zero. This cooling provides direct evidence that the universe has been expanding and cooling throughout its history. The patterns of temperature variation in the cosmic microwave background also reveal crucial information about the fundamental properties of the universe. By analyzing these patterns with exquisite precision, scientists can determine the exact amounts of ordinary matter, and dark energy that make up the cosmos. These measurements provide an independent confirmation of the dark energy discovered through supernova observations. The agreement between these different methods of studying cosmic expansion provides confidence that our understanding, while incomplete, is on the right track. Whether scientists study distant supernovas, the clustering of galaxies, or the cosmic microwave background, they get consistent results about the expansion rate and the influence of dark energy. This consistency is particularly remarkable, given that these different methods probe cosmic expansion in completely different ways. Supernovas act like cosmic lighthouses, providing direct measurements of distance and recession velocity. Galaxy clustering reveals the growth of cosmic structure over time. The cosmic microwave background carries information about the universe when it was incredibly young and dense. The fact that all these approaches tell the same basic story about cosmic expansion and dark energy provides strong evidence that scientists are correctly interpreting what they observe. While mysteries remain about the fundamental nature of dark energy, there is little doubt that it exists and drives the acceleration of cosmic expansion. As you settle deeper into rest tonight, this cosmic expansion continues its patient work on scales almost beyond imagination. In galaxy clusters hundreds of millions of light years away, space grows larger by thousands of kilometers every second. Yet this same expansion has virtually no effect on the space within our solar system, our planet, or your own body, protected as they are by forces much stronger than the gentle influence of dark energy. The mathematics that describe cosmic expansion reveal a universe of extraordinary precision and beauty. Einstein's equations of general relativity predict not just that space should expand or contract, but exactly how that expansion should proceed under different conditions. The observations match these mathematical predictions with remarkable accuracy, confirming our understanding of how gravity, matter, and dark energy work together to shape cosmic evolution. These equations also reveal deep connections between seemingly unrelated phenomena. The same mathematical framework that describes how matter curves space-time near a black hole also governs the expansion of the universe as a whole. The quantum mechanical principles that govern the behavior of individual atoms may also play a role in generating the dark energy that drives cosmic acceleration. Such connections suggest that the universe operates as a single integrated system, where every part influences every other part. The expansion of space affects the formation of galaxies, which influences the creation of stars, which determines the production of heavy elements, which makes possible the chemistry of life. Everything is connected in an intricate web of cause and effect that extends from the smallest scales to the largest. This cosmic interconnectedness extends to your own existence in ways both profound and subtle. The expansion of the universe has created the conditions necessary for complexity to emerge and flourish. Without cosmic expansion, gravity would have caused everything to collapse into black holes long before stars could form and create the elements necessary for planets and life. The precise balance between expansion and gravitational collapse has allowed billions of years for cosmic evolution to unfold. Stars have had time to form, live their lives and die, enriching space with the heavy elements created in their nuclear cores. Galaxies have had time to grow and evolve, creating the complex structures we see today. And life has had time to emerge and develop the consciousness that allows us to study and contemplate the cosmos itself. The rate of cosmic expansion plays a crucial role in this cosmic evolution. If the universe had expanded much faster after the Big Bang, matter would have been spread so thin that gravity could never have pulled it together into stars and galaxies. If it had expanded much slower, everything would have collapsed back together before complex structures could form. Instead, the expansion has proceeded at just the right rate to allow the delicate dance between expansion and gravity that has created the rich tapestry of cosmic structure we observe today. This balance continues to shape the universe around you, creating new possibilities for complexity and consciousness to emerge from the quantum fluctuations that permeate even the emptiest regions of space. The future that cosmic expansion promises is one of continued growth and evolution, unfolding over timescales that stretch far beyond human experience. As dark energy continues to drive acceleration, the universe will become larger, cooler, and in some ways more spacious, with vast gulfs of expanding space separating the islands of matter and light. Yet this future also holds promise for new forms of beauty and complexity. The same physical processes that operate today will continue to function in the expanding cosmos of tomorrow. Gravity will still collect matter into new structures. Nuclear fusion will still power the hearts of stars. And the fundamental constants that govern chemistry and biology will remain unchanged, preserving the possibility for life and consciousness to continue their cosmic journey. The expansion of space provides a kind of cosmic guarantee that there will always be room for new possibilities to emerge. As the universe grows larger, it creates infinite space for matter and energy to explore new forms of organization and complexity. The creative potential of the cosmos is as boundless as space itself, expanding along with the universe that contains it. This perspective offers a profound sense of cosmic optimism. While individual stars may die and individual planets may become uninhabitable, the universe as a whole continues to provide opportunities for new forms of life and consciousness to emerge. The expansion of space ensures that the cosmic story will continue to unfold, creating new chapters in the grand narrative of cosmic evolution. Recent discoveries have begun to reveal how this story might unfold in unexpected ways. Observations of the cosmic web, the largest structures in the universe, show how galaxies are connected by vast filaments of dark matter that stretch across hundreds of millions of light years. As the universe expands, these filaments grow longer and more tenuous, but they continue to channel matter toward the nodes where new galaxies form. The expansion also affects how information travels across the cosmos. Light signals between distant galaxies take longer and longer to traverse the growing distances, eventually stretching communication times to billions of years. In some sense, the expansion of space is gradually isolating different regions of the universe from each other, creating cosmic islands that will eventually lose contact with the broader universe. Yet even this cosmic isolation doesn't represent an end to possibility. Each isolated region will contain enough matter and energy to continue its own independent evolution for trillions of years to come. New stars will form, new planets will condense, and new opportunities for complexity will emerge within each cosmic island, even as the space between islands continues to grow. The timescales involved in these processes are so vast, they challenge human comprehension. The current age of the universe, 13.8 billion years, represents only a tiny fraction of the time available for future cosmic evolution. Stars like our Sun will continue to shine for billions of years more. Red dwarf stars, the most common type in the universe, can burn steadily for trillions of years, providing stable energy sources for planetary systems throughout the cosmic future. Even after the last stars have exhausted their nuclear fuel, the universe will continue to evolve through processes we can barely imagine. Protons themselves may eventually decay, though this would take inconceivably long periods of time. Black holes will slowly evaporate through Hawking radiation, returning their matter and energy to space over periods that dwarf the current age of the universe by factors of trillions upon trillions. These distant futures may seem almost like science fiction, but they emerge naturally from our current understanding of physics and cosmic expansion. The same laws that govern the behavior of matter and energy today will continue to operate in the far future, ensuring that the universe remains a place where interesting things can happen, even on the longest imaginable timescales. As you drift toward deeper rest, you can find comfort in this cosmic constancy. The physical laws that describe how space expands, how gravity works, how energy flows, and how matter organizes itself operate with perfect reliability across all scales of space and time. The universe follows rules that we can study and understand, even when the full implications of those rules extend far beyond our direct experience. The expansion of space proceeds according to these same reliable principles. Dark energy maintains its influence with mathematical precision, driving acceleration at exactly the rate predicted by Einstein's equations. The relationship between distance and recession velocity follows Hubble's law with remarkable consistency across billions of light years of space. This predictability allows scientists to trace the expansion both backward and forward in cosmic time. Looking into the past, we can see how the universe has evolved from its hot, dense beginning through the formation of the first atoms, the first stars, and the first galaxies. Looking toward the future, we can predict how expansion will continue to shape cosmic evolution for billions of years to come. The story that emerges from these observations and calculations is one of a universe that has been expanding and cooling for nearly 14 billion years, gradually creating the conditions necessary for increasing complexity and consciousness. From the simple hydrogen and helium created in the first few minutes after the Big Bang, cosmic evolution has produced the full periodic table of elements, rocky planets, liquid water, and eventually life itself. This progression from simplicity to complexity occurs against the backdrop of continued cosmic expansion. As space grows larger and matter becomes more spread out, gravity works to collect that matter into ever more intricate structures. The interplay between expansion and gravitational collapse has created the hierarchical organization of the cosmos, from planets to stars, to galaxies, to galaxy clusters. Each level of this hierarchy operates according to different physical principles, yet all are connected through the common framework of expanding spacetime. Quantum mechanics governs the behavior of individual atoms. Electromagnetic forces bind atoms into molecules and molecules into complex structures. Gravity shapes the large-scale architecture of the universe, and dark energy drives the overall expansion that provides the stage for all other cosmic processes. Understanding these connections has been one of the great achievements of modern science. The same mathematical language that describes the motion of planets also describes the expansion of space. The same principles that govern chemical reactions in a laboratory also operate in the atmospheres of distant planets. The universe operates as a unified whole, following consistent laws across all scales of space and time. This unity provides a profound sense of cosmic belonging. You are not separate from the universe around you, but rather an integral part of its ongoing evolution. The atoms in your body were created in the nuclear furnaces of ancient stars. The energy that powers your thoughts comes ultimately from fusion reactions in the core of the sun. The gravitational field that holds you gently against your bed extends throughout the cosmos, connecting you to every other piece of matter in the universe. The expansion of space has played a crucial role in making your existence possible. Without cosmic expansion, the universe would have collapsed long before stars could form and create the heavy elements necessary for planets and life. The precise balance between expansion and gravitational attraction has created a cosmos where complexity can emerge and flourish over billions of years. This same expansion continues to shape the cosmic environment around you. As you sleep, new regions of space come into existence through the stretching of space-time itself. These new regions provide additional volume for matter and energy to occupy, contributing to the overall growth and evolution of the cosmos. The process occurs with perfect smoothness and continuity. Space doesn't expand in sudden jumps or violent motions, but rather grows steadily and predictably according to the mathematical laws that govern cosmic evolution. The expansion rate can be precisely calculated using Einstein's equations, and observations confirm these calculations with extraordinary accuracy. This mathematical precision reveals something beautiful about the nature of cosmic expansion. It's not a chaotic or random process, but rather the natural expression of the fundamental structure of space-time itself. The universe expands because expansion is written into the very geometry of space and time, just as the angles of a triangle are determined by the curvature of the surface on which it's drawn. Einstein's theory of general relativity shows that space and time form a unified fabric that can bend, stretch, and curve in response to matter and energy. Cosmic expansion represents the large-scale geometry of this space-time fabric, shaped by the distribution of matter and dark energy throughout the universe. The expansion is as natural and inevitable as the curvature of space around a massive object like the sun. This geometric perspective on cosmic expansion provides a deeper understanding of why galaxies appear to move away from each other. They're not racing through space like objects thrown by an explosion. Instead, they're following the natural geometry of expanding spacetime, like points marked on a balloon that move apart as the balloon inflates. The balloon analogy, while imperfect, helps illustrate why observers in any galaxy would see all other galaxies moving away from them, just as any point on an expanding balloon sees all other points moving away. Any observer in the expanding universe sees all distant galaxies receding according to Hubble's law. There is no center to the expansion, no special location from which everything else is moving away. This universal perspective on cosmic expansion reveals something profound about our place in the universe. Earth is not at the center of cosmic expansion, nor is the Milky Way galaxy or our local group of galaxies. We exist within a vast cosmic democracy where every observer, from every vantage point, witnesses the same fundamental pattern of universal growth. This democratic nature of cosmic expansion extends to the very measurements that reveal it. When astronomers calculate the expansion rate of the universe, they arrive at a number known as the Hubble constant. This value tells us how fast space is growing at the present moment, measured in kilometers per second per megaparsec, a unit that captures the relationship between distance and recession velocity across cosmic scales. The current best measurements suggest that space is expanding at a rate of about 70 kilometers per second for every megaparsec of distance. A megaparsec represents roughly 3.25 million light-years, a distance so vast that light itself takes more than 3 million years to cross it. At this rate of expansion, two galaxy clusters separated by such a distance are moving apart at 70 kilometers per second due to the growth of space between them. To put this in perspective that connects to your nightly rest, consider that in the 8 hours you spend sleeping, the space between these distant galaxy clusters grows by about 2 million kilometers. This represents a distance equivalent to traveling from the Earth to the Moon and back again more than twice. Yet this enormous growth occurs so smoothly and gradually that it can only be detected through the most sensitive astronomical instruments. The precision required to measure cosmic expansion pushes the boundaries of human technological capability. Scientists must account for countless subtle effects that could influence their observations. The motion of Earth around the Sun's orbit through the Milky Way's motion through our local group of galaxies, all of these movements must be carefully subtracted from the measurements to reveal the underlying cosmic expansion. Even the expansion of space itself occurs at different rates in different directions. Though these variations are incredibly small, the universe is remarkably uniform on large scales, but sensitive measurements can detect tiny deviations from perfect smoothness. These minute irregularities reflect the quantum fluctuations that existed in the very early universe, stretched to cosmic scales by billions of years of expansion. As you settle into deeper rest tonight, these quantum origins of cosmic structure provide a profound connection between the smallest and largest scales of reality. The same uncertainty principle that governs individual atoms also played a role in creating the galaxy clusters and cosmic voids that stretch across billions of light-years. The universe operates as a single, interconnected system where quantum mechanics and general relativity work together to create the cosmos we observe. The expansion of space also reveals something remarkable about the nature of time itself. Because light travels at a finite speed, looking deeper into space means looking further back in time. When astronomers observe distant galaxies, they see them as they existed billions of years ago, when the universe was younger and smaller. This creates a kind of cosmic time machine, allowing scientists to study the history of expansion directly. The most distant galaxies observable today appear to us as they were when the universe was less than 1 billion years old. At that time, the cosmos was much more compact than it is today, and the rate of expansion was quite different. By comparing galaxies at different distances and ages, astronomers can trace how the expansion rate has changed throughout cosmic history. This historical perspective reveals that the expansion of space has not proceeded at a constant rate. In the universe's youth, the expansion was actually slowing down as gravity worked to pull matter back together. The turning point came approximately 5 billion years ago, when dark energy began to dominate cosmic evolution and drive accelerated expansion. The transition from decelerated to accelerated expansion represents one of the most significant events in cosmic history. It marked the moment when the outward push of dark energy overtook the inward pull of gravity on cosmic scales. Since that transition, the expansion has been speeding up, and current observations suggest this acceleration will continue indefinitely into the future. Understanding this cosmic timeline helps place your own existence in its proper context. The solar system formed approximately 4.5 billion years ago, right around the time when cosmic expansion was transitioning from deceleration to acceleration. The Earth condensed from a disk of gas and dust at roughly the same time that dark energy was beginning to take control of cosmic evolution. Life appeared on Earth several billion years later, emerging in a universe that was already dominated by dark energy and expanding at an accelerating rate. Every moment of biological evolution, from the first simple cells to the development of consciousness, has occurred against the backdrop of accelerating cosmic expansion. You exist in an epoch when the universe is growing faster and faster, creating ever more space for new possibilities to emerge. This cosmic context provides a profound perspective on the relationship between local and universal processes. While the universe expands on the larger scales, the fundamental forces that govern chemistry and biology remain unchanged. The electromagnetic forces that bind atoms into molecules operate with the same strength today as they did billions of years ago. The nuclear forces that power the sun burn with the same intensity regardless of cosmic expansion. This constancy of physical laws ensures that life can flourish even in an expanding universe. The expansion affects only the largest scales of cosmic structure, leaving the architecture of smaller systems essentially unchanged. Stars continue to shine, planets maintain their orbits, and biological processes proceed normally, all while embedded in a cosmos that grows larger every moment. The protection that gravity provides against cosmic expansion extends to increasingly larger scales. Individual atoms remain the same size because the electromagnetic forces that bind electrons to nuclei are enormously stronger than the influence of dark energy. Planets stay in stable orbits because the sun's gravitational field dominates the local space-time geometry. Even entire galaxies remain intact because their internal gravitational forces overcome the gentle tug of cosmic expansion. Only on the largest scales, where the distances between galaxy clusters span hundreds of millions of light years, does cosmic expansion become the dominant influence. These vast regions of space, largely empty except for the occasional galaxy or cluster, provide the stage where dark energy can work most effectively to drive accelerated expansion. The cosmic web of structure that spans these larger scales reveals the interplay between expansion and gravity in creating the universe we observe today. Computer simulations show how tiny quantum fluctuations in the early universe grew over billions of years into the complex network of filaments and voids that characterize cosmic structure. Gravity worked to amplify small density variations, pulling matter together along preferred directions to create the web-like pattern of galaxy distribution. As expansion continued and space grew larger, this cosmic web stretched along with it. The filaments that connect galaxy clusters became longer and more tenuous, while the voids between them grew ever more empty. Yet the basic architecture remained intact, preserved by the gravitational forces that initially created it. This cosmic web continues to evolve today as expansion carries its components farther apart. New computer simulations suggest that billions of years in the future, the web will become increasingly fragmented as accelerating expansion overcomes the gravitational forces that currently hold it together. Eventually, each galaxy cluster may become isolated, surrounded by vast regions of empty space with no connection to the broader cosmic structure. Yet even in this distant future, The basic processes that create complexity and support life will continue to operate within each isolated region. Galaxy clusters contain enough matter to fuel star formation for trillions of years to come. The gravitational collapse of gas clouds will continue to create new stars, and planetary systems will continue to form around those stars, preserving the possibility for life and consciousness to emerge and flourish. The timescales involved in these future scenarios stretch far beyond human comprehension. The current age of the universe represents only a tiny fraction of the time available for future cosmic evolution. Red dwarf stars, which make up the majority of stars in the universe, can burn steadily for hundreds of times longer than the universe has currently existed. This provides enormous spans of time for biological evolution to explore new forms of complexity and consciousness. Even the expansion of space itself may not continue forever in its current form. Some theories suggest that dark energy might change its behavior over cosmic time, potentially leading to different phases of cosmic evolution in the far future. While current observations show dark energy remaining remarkably constant, future measurements may reveal subtle changes that could alter the ultimate fate of the universe. These possibilities remind us that cosmic expansion represents an ongoing story rather than a predetermined outcome. The universe continues to evolve and surprise us, revealing new aspects of its behavior as our observational capabilities improve. Each new discovery adds another piece to the cosmic puzzle, gradually building a more complete picture of how space, time, matter, and energy work together to create the cosmos we inhabit. The instruments that enable these discoveries represent marvels of human engineering and scientific collaboration. The James Webb Space Telescope, positioned at a gravitationally stable point far beyond Earth's orbit, can detect infrared light from galaxies so distant that their visible light has been redshifted beyond the range of human vision. Its mirrors are polished to such precision that they deviate from perfect smoothness by less than a billionth of a meter. Ground-based observatories use adaptive optic systems to compensate for the blurring effects of Earth's atmosphere, creating images sharper than those possible from space just a few decades ago. Arrays of radio telescopes spread across continents work together to create virtual instruments with the resolving power of a telescope the size of the Earth itself. These technological achievements allow astronomers to study cosmic expansion with unprecedented precision and detail. The data collected by these instruments flows to scientists around the world, who work together to analyze and interpret the observations. This global collaboration ensures that no single measurement or interpretation goes unchallenged. Every significant discovery is independently verified by multiple research groups using different techniques and instruments. The result is a robust understanding of cosmic expansion that reflects the collective effort of thousands of dedicated researchers. This collaborative approach has been essential to understanding the subtle effects of cosmic expansion. The acceleration driven by dark energy is so gentle that it can only be detected through the most careful statistical analysis of large data sets. Individual measurements may show significant uncertainties, but when combined with hundreds or thousands of similar observations, clear patterns emerge that reveal the underlying cosmic processes. The statistical nature of these measurements reflects a deeper truth about scientific knowledge. Our understanding of cosmic expansion doesn't depend on any single observation or theoretical insight, but rather emerges from the convergence of many independent lines of evidence. Supernova observations, galaxy clustering measurements, cosmic microwave background studies, and theoretical calculations all point toward the same basic picture of an accelerating universe dominated by dark energy. This convergence provides confidence that our understanding, while incomplete, correctly captures the essential features of cosmic expansion. Even if future observations reveal new complexities or unexpected behaviors, the basic framework of expanding spacetime driven by dark energy seems likely to remain valid. Science progresses by building upon previous discoveries rather than completely overturning them, gradually refining our understanding as new data becomes available. As you rest peacefully tonight, this scientific process continues around the globe. Telescopes in Chile capture light from distant supernovas, while observatories in Hawaii measure the positions of nearby galaxies. Satellites in space monitor the cosmic microwave background radiation, while supercomputers on Earth simulate the evolution of cosmic structure over billions of years. The collective effort to understand cosmic expansion never stops, driven by human curiosity about our place in the universe. The expansion of space provides a profound context for contemplating the meaning and significance of consciousness in the cosmos. You represent the universe becoming aware of itself, matter and energy, organized in such a way that it can contemplate its own origins and evolution. The atoms in your brain were forged in stellar cores billions of years ago, scattered into space by supernovas, and eventually assembled into the complex structures that enable thought and awareness. This process of cosmic self-awareness has occurred against the backdrop of universal expansion. Every moment of biological evolution, from the first self-replicating molecules to the development of consciousness, has taken place in an expanding cosmos. The growth of complexity and awareness has proceeded hand in hand with the growth of space itself, suggesting deep connections between cosmic evolution and the emergence of consciousness. The expansion of space ensures that this process can continue indefinitely into the future. As the universe grows larger, it creates more room for matter and energy to explore new forms of organization and complexity. The same quantum fluctuations that may drive dark energy also provide the fundamental randomness necessary for creative evolution and the emergence of new forms of awareness. Recent discoveries in astrobiology suggest that the conditions necessary for life may be quite common throughout the universe. Rocky planets orbit in the habitable zones around their stars, where liquid water can exist on planetary surfaces. The chemical elements necessary for biology are abundant in space, created in stellar cores and distributed by cosmic processes. The expansion of space has helped spread these building blocks of life throughout the cosmos, seeding countless worlds with the raw materials for biological evolution. As cosmic expansion continues, it will carry these potentially life-bearing worlds farther apart, creating vast islands of evolution that develop independently over cosmic time. Each island may explore different pathways toward complexity and consciousness, creating a universe rich with diverse forms of awareness and understanding. The expansion of space doesn't limit the potential for life and consciousness, but rather multiplies the opportunities for their emergence. This cosmic perspective on consciousness provides a profound sense of connection and purpose. You are not an isolated accident in an indifferent universe, but rather an integral part of the cosmos coming to understand itself. Your thoughts and experiences contribute to the universe's growing self-awareness, adding to the collective understanding of cosmic processes and the nature of existence itself. The expansion of space continues this cosmic journey of discovery, creating ever more opportunities for new forms of consciousness to emerge and contribute their unique perspectives to the universal story. Each new world, each new form of life, each new type of awareness adds another chapter to the ongoing narrative of cosmic evolution and self-discovery. As you settle into deeper rest, you can take comfort in knowing that you participate in this grand cosmic story. Your existence connects you to processes that operate on the largest scales of space and time, while your consciousness represents one of the universe's most remarkable achievements. The same expansion that carries distant galaxies apart also provides the cosmic context within which awareness and understanding can flourish. The mathematical elegance that governs cosmic expansion reflects something beautiful about the underlying structure of reality. Einstein's equations reveal that space and time form a unified fabric that responds to matter and energy in predictable, calculable ways. The expansion of this space-time fabric follows precise mathematical laws that allow scientists to trace cosmic evolution from the Big Bang to the present and project it into the distant future. This mathematical precision suggests that the universe operates according to deep principles of order and harmony. The same geometric relationships that describe the curvature of space around a massive star also govern the expansion of the cosmos as a whole. The universe reveals itself to be not chaotic or random, but rather organized according to elegant mathematical principles that the human mind can discover and understand. The fact that consciousness can comprehend these cosmic processes represents one of the most remarkable aspects of universal evolution. Through billions of years of expansion and cooling, the universe has created conditions that allow matter to organize itself into forms capable of understanding cosmic expansion itself. You represent the cosmos developing the ability to study and appreciate its own magnificent architecture. This self-referential quality of cosmic evolution suggests that consciousness and understanding play fundamental roles in the universe's development. The expansion of space has created the conditions necessary for awareness to emerge, and awareness, in turn, allows the universe to understand and appreciate its own expansion. The cosmic story becomes complete only when consciousness emerges to witness and comprehend the processes that created it. The expansion of space also provides a natural rhythm that connects your personal experience to cosmic processes. Just as your breathing follows natural cycles of inhalation and exhalation, the universe follows cycles of expansion and structure formation that span billions of years. Your heartbeat echoes the steady pulse of stellar nucleosynthesis, the fusion processes that create new elements in the cores of massive stars. These connections between personal and cosmic rhythms suggest that you are intimately connected to the universe around you. The same physical laws that govern the expansion of space also operate within your body, maintaining the delicate balance of forces that make life possible. The electromagnetic interactions that power your nervous system are governed by the same principles that determine how atoms behave in distant galaxies. Even the flow of time that carries you through your daily experience is connected to the cosmic expansion that stretches space on the largest scales. Einstein's theory of relativity reveals that space and time are inseparably linked, forming a unified space-time fabric that expands as the universe evolves. Your personal timeline unfolds within this expanding cosmic context, connecting your individual existence to the grand sweep of universal history. As you drift toward deeper rest, you can feel yourself as part of this cosmic rhythm. Your breathing slows to match the patient pace of stellar evolution. Your heartbeat synchronizes with the steady expansion of space. Your thoughts flow like galaxies, carried apart by the gentle growth of the universe itself. In sleep, you participate directly in the cosmic process of rest and renewal that allows complexity and consciousness to flourish. The expansion of space continues throughout the night while you sleep, carrying distant galaxies millions of kilometers farther apart by the time morning arrives. This cosmic growth provides the backdrop for all the dreams and restoration that occur during your rest. While your consciousness retreats from waking awareness, the universe continues its ancient work of expansion and evolution, preparing the cosmic stage for another day of possibility and discovery. When you wake tomorrow morning, you will open your eyes to a universe that is measurably larger than the one you left when you closed them. New light will have arrived from distant galaxies, carrying information about cosmic processes that occurred billions of years ago. The cosmic microwave background radiation will have continued its journey from the edge of the observable universe, bringing us messages from the time when atoms first formed and the cosmos became transparent to light. Throughout all of this cosmic activity, the fundamental processes that make life and consciousness possible will continue to operate with perfect reliability. The sun will continue to shine with the steady nuclear fire that has warmed our planet for billions of years. The Earth will maintain its stable orbit, protected by gravitational forces that are far stronger than the gentle influence of cosmic expansion. The atoms in your body will retain their same sizes and properties, unaffected by the growth of space on cosmic scales. This constancy within change provides a profound sense of cosmic security. While the universe expands and evolves on the larger scales, the local environment that supports life remains stable and predictable. The same physical laws that govern atomic behavior today will continue to operate tomorrow and for billions of years into the future. The expansion of space enhances rather than threatens the conditions necessary for complexity and consciousness. The cosmic web of structure that spans the observable universe will continue to evolve as expansion carries its components farther apart. New stars will form in distant galaxies while others exhaust their nuclear fuel and die, enriching space with the heavy elements necessary for future generations of stars and planets. The cycle of stellar birth and death will continue for trillions of years, providing countless opportunities for new worlds to form and new forms of life to emerge. Even the mysterious dark energy that drives cosmic acceleration operates according to natural laws that ensure the expansion proceeds smoothly and predictably. While scientists don't yet understand the fundamental nature of dark energy, they can measure its effects with extraordinary precision and use those measurements to predict how expansion will continue in the future. The universe follows rules that we can discover and understand, even when those rules involve phenomena that remain mysterious. This combination of mystery and understanding reflects the ongoing nature of scientific discovery. Each new observation reveals previously unknown aspects of cosmic expansion, while confirming the basic framework of expanding space-time governed by general relativity. The universe continues to surprise us with its complexity and elegance, revealing new layers of organization and beauty as our observational capabilities improve. Future space missions will extend our ability to study cosmic expansion even further into the past and with greater precision. Next-generation telescopes will be able to observe the very first galaxies that formed after the Big Bang, revealing how cosmic expansion influenced the earliest phases of structure formation. Advanced gravitational wave detectors may be able to measure ripples in space-time itself, providing new ways to study the geometry and expansion of the cosmos. These future discoveries will undoubtedly reveal new complexities and unexpected behaviors in cosmic expansion. Science progresses through a continuous cycle of observation, theory, and discovery that gradually builds a more complete understanding of natural processes. Each new finding adds to our knowledge, while often raising new questions that drive further investigation. The expansion of space provides a perfect example of how scientific understanding develops over time. Einstein's original equations predicted that the universe should be either expanding or contracting, but Einstein himself initially doubted this result and added a cosmological constant to maintain a static universe. When Hubble's observations revealed that galaxies were indeed moving apart, Einstein called his cosmological constant his greatest blunder. Ironically, the discovery of dark energy and cosmic acceleration has rehabilitated Einstein's cosmological constant as a possible explanation for the mysterious force that drives expansion. The same mathematical term that Einstein added to prevent expansion may actually describe the dark energy that accelerates it. This twist in the history of cosmology illustrates how scientific understanding often develops in unexpected ways, with discarded ideas sometimes returning in new forms. The story of cosmic expansion also demonstrates the power of international scientific collaboration. The discoveries that revealed acceleration required observations from telescopes around the world, combined with theoretical insights from physicists in many different countries. The measurement of cosmic expansion continues today through collaborations that span continents and involve thousands of researchers working together toward common goals. This global effort to understand cosmic expansion reflects humanity's collective curiosity about our place in the universe. Regardless of nationality, culture, or background, humans share a deep fascination with the cosmos and our connection to it. The expansion of space provides a unifying framework that connects all conscious beings to the same cosmic processes and the same universal story of evolution and growth. As you rest tonight in the expanding universe, you participate in this ancient human quest to understand the cosmos. Your consciousness represents the universe developing the ability to study itself, while your rest provides the restoration necessary for continued learning and discovery. The expansion of space continues around you with the same patient rhythm that has characterized cosmic evolution since the beginning of time. The cosmic microwave background radiation that fills all of space carries the imprint of quantum fluctuations from the universe's earliest moments, stretched to cosmic scales by billions of years of expansion. These tiny variations in temperature represent the seeds from which all cosmic structure has grown, including the galaxy that contains our solar system and the planet on which you rest. The expansion of space has transformed these microscopic quantum fluctuations into the magnificent cosmic web that spans billions of light years. Gravity has worked within this expanding framework to create galaxies, stars, and planets, while cosmic expansion has provided the time and space necessary for complexity to emerge and consciousness to develop. Tomorrow you will wake to participate once again in this cosmic story of discovery and understanding. The same expansion that carries distant galaxies apart also provides the context within which human knowledge and awareness can grow. Each new day brings opportunities to learn more about cosmic processes and to appreciate more fully our connection to the expanding universe that surrounds us. The gentle rhythm of cosmic expansion provides a profound backdrop for human existence. Like the turning of seasons or the rise and fall of ocean tides, the growth of space follows natural cycles that connect personal experience to universal processes. As you surrender to sleep, you align yourself with cosmic rhythms that have been operating since the beginning of time and will continue long after individual lives have ended. In this expanding universe, there is always room for new possibilities, new discoveries, and new forms of beauty to emerge. The growth of space ensures that the cosmic story will continue to unfold, creating new chapters in the grand narrative of universal evolution. Your rest tonight contributes to this ongoing story, providing the renewal necessary for consciousness to continue its cosmic journey of discovery and understanding. The expansion of space proceeds with perfect patience and reliability, following mathematical laws that ensure cosmic evolution continues smoothly and predictably. While you sleep, distant galaxies move millions of kilometers farther apart. Space itself grows larger, and the universe takes another small step in its ancient journey from simplicity to complexity, from unconsciousness to awareness, from isolation to understanding. Sleep peacefully in this expanding cosmos, knowing that its growth creates infinite opportunities for wonder, discovery, and connection. The universe expands while you rest, and in that expansion lies the promise of tomorrow and all the tomorrows yet to come, stretching out into a future as vast and full of potential as the cosmos itself. Of potential as the cosmos itself. The story we've been following together tonight, this gentle tale of cosmic expansion unfolding while you rest, brings us now to consider what all of this means for the most distant reaches of space and time. As your breathing settles into its natural rhythm and your body finds deeper comfort, let's explore the edges of what we can observe, where the expansion of space reveals its most profound secrets. At the very limits of what our most powerful telescopes can detect, we encounter galaxies so far away that their light has been traveling toward us for more than 13 billion years. These distant beacons show us the universe as it existed when it was less than 1 billion years old, a cosmic infant compared to its current age of 13.8 billion years. The light from these ancient galaxies carries within it the story of how cosmic expansion has shaped the universe throughout most of its history. When astronomers observe these incredibly distant galaxies, they see something remarkable. The light has been stretched so much by cosmic expansion during its long journey that what began as visible starlight has been redshifted all the way into the infrared portion of the electromagnetic spectrum. It's as if the universe has taken the blue and green light of ancient stars and gently pulled it like taffy until it becomes the deep red glow that our instruments can barely detect. This extreme redshift tells us that space has expanded by more than 10 times its original size since that light began its journey. The universe was much smaller and more compact when these photons first left their parent galaxies. Every cubic meter of space that existed then has grown into more than 1,000 cubic meters today, carrying those distant galaxies along like leaves floating on the surface of an ever-expanding cosmic ocean. The mathematics of this expansion follow patterns so elegant they seem almost musical in their harmony. Einstein's field equations describe how the fabric of space-time responds to the presence of matter and energy, predicting not just that the universe should expand, but precisely how that expansion should unfold under different conditions. When scientists solve these equations using the actual amounts of matter and dark energy observed in our cosmos, they get results that match astronomical observations with breathtaking accuracy. This mathematical precision reveals something profound about the nature of reality itself. The same geometric principles that describe how space curves around a massive star also govern the expansion of the entire universe. Space and time form a unified fabric that bends and stretches according to universal laws, creating the cosmic architecture within which all matter and energy must exist. The expansion affects this cosmic architecture in ways both subtle and profound. On the largest scales, where dark energy dominates, space stretches freely and galaxy clusters drift apart like islands in an expanding sea. But on smaller scales, where gravity maintains its grip, structures remain bound together despite the overall growth of the universe around them. This creates a kind of cosmic hierarchy, where different scales of organization respond differently to expansion. Individual atoms remain unchanged because the electromagnetic forces that bind electrons to nuclei are vastly stronger than the influence of dark energy. Planets maintain their orbits because stellar gravity dominates the local geometry of space-time. Even entire galaxies stay intact because their internal gravitational fields overcome the gentle tug of cosmic expansion. Only when we consider the vast distances between galaxy clusters, spanning hundreds of millions of light years, does cosmic expansion become the dominant influence. In these enormous voids, where matter is spread incredibly thin, dark energy can work most effectively to drive the acceleration we observe today. Recent observations have begun to map these cosmic voids with unprecedented detail, revealing them to be among the largest and most empty structures in the universe. Some voids stretch across distances so vast that light takes hundreds of millions of years to cross them. Within these regions, matter is so sparse that you might travel for millions of light years without encountering a single galaxy. Yet even these seemingly empty regions are not truly vacant. They contain the same dark energy that permeates all of space, maintaining its constant density as expansion creates ever more volume. They're also filled with the cosmic web of dark matter, invisible filaments that connect distant galaxy clusters and provide the scaffolding along which ordinary matter organizes itself into the structures we can observe. As cosmic expansion continues, these voids will grow ever larger and more empty, while the filaments that connect galaxy clusters will become increasingly stretched and tenuous. Computer simulations suggest that billions of years from now, the cosmic web may become so elongated that its connections begin to break, leaving galaxy clusters isolated in vast oceans of expanding space. This gradual fragmentation of cosmic structure represents one possible future for our expanding universe. As dark energy continues to drive acceleration, the distances between galaxy clusters will grow so large that they lose all gravitational influence on each other. Each cluster will become a cosmic island, containing perhaps thousands of galaxies, but separated from all other clusters by gulfs of space that grow larger with each passing eon. Yet within each isolated cluster, the familiar processes of cosmic evolution will continue for trillions of years to come. New stars will form from clouds of gas and dust. Planets will condense around young suns, and the chemistry necessary for life will continue to operate according to the same physical laws that govern these processes today. The expansion of space ensures that there will always be room for new possibilities to emerge, even as it gradually isolates different regions of the universe from each other. The timescales involved in these cosmic processes stretch beyond easy comprehension. The current age of the universe represents only the opening chapter in a story that may continue for periods longer than current physics can meaningfully describe. Red dwarf stars, which make up the majority of stars in our galaxy, burn their nuclear fuel so slowly that they can shine steadily for hundreds of times longer than the universe has currently existed. This provides vast spans of time for biological evolution to explore new forms of complexity and consciousness. Even after our sun exhausts its fuel and becomes a white dwarf star, countless other stars will continue to provide stable energy sources for planetary systems throughout the cosmos. The expansion of space doesn't limit these possibilities, but rather multiplies them, creating ever more volume for matter and energy to organize themselves in novel ways. Some theories suggest that even the protons and neutrons that make up ordinary matter may not be perfectly stable over these enormous timescales. If current ideas about the unification of fundamental forces are correct, these particles might eventually decay, though this would occur over periods so long that they dwarf even the vast future lifetime of red dwarf stars. Even in such a distant future, when all ordinary matter has decayed and only black holes remain, the expansion of space would continue according to the same mathematical laws that govern it today. Stephen Hawking's theoretical work suggests that even black holes eventually evaporate through a quantum mechanical process, returning their mass and energy to space over periods that exceed the current age of the universe by factors of trillions upon trillions. These almost unimaginable futures emerge naturally from our current understanding of physics and cosmology. They represent the logical extension of processes that operate today, projected forward across timescales that challenge human comprehension. Yet the same equations that describe cosmic expansion on these vast scales also govern the gentle growth of space that occurs while you rest tonight. The reliability of these physical laws provides a deep sense of cosmic stability. The same principles that will govern the universe's evolution over trillions of years also ensure that your local environment remains stable and predictable from one day to the next. The expansion of space follows mathematical rules, so precise that scientists can use them to predict cosmic evolution across the entire future history of the universe. This mathematical precision also allows astronomers to look backward through cosmic time, tracing the expansion all the way to its beginning in the Big Bang. By measuring how fast space is expanding today and understanding how that rate has changed over cosmic history, scientists can determine exactly when the expansion began and what conditions were like in the universe's earliest moments. The cosmic microwave background radiation provides a direct window into this ancient past. This faint glow, detectable in every direction we look, shows us the universe as it appeared when it was only 380,000 years old. At that time, the cosmos had cooled enough for the first atoms to form, making space transparent to light for the first time in cosmic history. The tiny temperature variations in this ancient radiation reveal the quantum fluctuations that existed in the very early universe. These microscopic irregularities, stretched to cosmic proportions by billions of years of expansion, became the seeds from which all cosmic structure has grown. Every galaxy, every star, every planet, including the Earth on which you rest tonight, can trace its origins back to these primordial quantum fluctuations. The connection between quantum mechanics and cosmic expansion reveals the deep unity that underlies all natural phenomena. The same uncertainty principle that governs the behavior of individual atoms also played a crucial role in creating the large-scale structure of the universe. The cosmic web that spans billions of light-years emerged from quantum processes operating on the smallest possible scales. This quantum origin of cosmic structure provides another profound connection between your existence and the expansion of space. The atoms in your body, the molecules that carry your thoughts, the very neurons that process these ideas about cosmic expansion, all owe their existence to quantum fluctuations that occurred in the first fraction of a second after the Big Bang. The expansion of space has carried these quantum seeds across billions of years of cosmic evolution, allowing them to grow into the complex structures that make life and consciousness possible. Without cosmic expansion, these primordial fluctuations would have remained microscopic. With too rapid expansion, they would have been stretched so thin that gravity could never have amplified them into galaxies and stars. The actual rate of expansion has been precisely calibrated to allow quantum fluctuations to grow into cosmic structure over billions of years of cosmic history. This delicate balance between expansion and gravitational collapse has created a universe where complexity can emerge and consciousness can develop the ability to contemplate its own cosmic origins. Recent advances in quantum field theory have begun to reveal even deeper connections between the expansion of space and the fundamental nature of reality. The vacuum of space itself, far from being truly empty, seethes with quantum activity. Virtual particles constantly appear and disappear, borrowing energy from the quantum field for brief moments before annihilating each other and returning that energy to the vacuum. Some theories suggest that this quantum activity in the vacuum might be related to the dark energy that drives cosmic acceleration. The energy density of the quantum vacuum could provide the constant pressure that pushes space to expand at an ever-increasing rate. However, when physicists calculate how much vacuum energy should exist, they get results that differ from observations by an enormous factor, highlighting how much mystery still surrounds both quantum mechanics and cosmic expansion. This quantum vacuum energy operates on scales far too small to affect your daily experience, yet it may play a fundamental role in shaping the cosmic environment within which you exist. Every cubic centimeter of space around you contains countless virtual particles appearing and disappearing in the quantum foam that underlies all of reality. These quantum processes occur trillions of times per second, yet their combined effect may be driving the gentle acceleration of cosmic expansion. The relationship between quantum mechanics and general relativity, between the very small and the very large, represents one of the greatest unsolved puzzles in modern physics. Scientists understand both quantum mechanics and general relativity extremely well within their respective domains, but combining them into a unified theory remains an active area of research that may ultimately reveal new insights about cosmic expansion and the nature of space and time. As you settle deeper into rest tonight, these quantum processes continue their invisible work throughout every atom of your body and every cubic centimeter of space around you. The same quantum fields that may drive cosmic expansion also enable the chemical reactions that sustain your life and the electrical signals that power your thoughts and dreams. The expansion of space provides the cosmic canvas on which all of these quantum processes play out. As the universe grows larger, it creates more volume for quantum fields to occupy, more space for virtual particles to appear and disappear, more room for the fundamental processes of nature to explore new possibilities and create new forms of order and complexity. This ongoing creation of space through cosmic expansion means that the universe you wake up to tomorrow morning will contain more volume than the universe you're resting in tonight. Somewhere in that new space, quantum fluctuations will be creating the seeds for future structure formation. New regions of space-time will be coming into existence, providing additional territory for matter and energy to organize themselves in ways that have never existed before. The cosmic microwave background radiation that fills all of space carries information about this process of creation and expansion. As you sleep, billions of photons from this ancient radiation are passing through your body every second, carrying messages from the time when the universe first became transparent to light. These photons have been traveling through expanding space for nearly 14 billion years, their wavelengths stretched by cosmic expansion from visible light to microwave radiation. Each of these cosmic messengers tells the same story about universal expansion and the creation of structure from primordial simplicity. They carry within their red-shifted wavelengths the history of how space has grown since the time when atoms first formed and light could travel freely through the cosmos. By studying this radiation with sensitive instruments, scientists can trace the expansion history of the universe with extraordinary precision. The patterns of temperature variation in the cosmic microwave background also reveal crucial information about the fundamental composition of the universe. The precise mixture of ordinary matter, dark matter, and dark energy determines how cosmic structure forms and evolves. By analyzing these ancient patterns, astronomers can measure the density of each component with remarkable accuracy. These measurements confirm that ordinary matter, the stuff that makes up stars, planets, and people, comprises less than 5% of the total energy density of the universe. Dark matter accounts for about 27%, while dark energy dominates with roughly 68%. This cosmic census reveals that the universe consists primarily of components that remain deeply mysterious to modern science. Yet despite these mysteries, the overall picture of cosmic expansion has become increasingly clear and consistent. Multiple independent lines of evidence, from supernova observations to galaxy clustering measurements to cosmic microwave background studies, all point toward the same basic conclusion. The universe is expanding at an accelerating rate, driven by a mysterious dark energy that permeates all of space. This convergence of evidence from different observational techniques provides strong confidence in our understanding of cosmic expansion, even though the fundamental nature of dark energy remains unknown. Science often progresses by establishing reliable empirical relationships before fully understanding the underlying physical mechanisms. The relationship between distance and recession velocity in cosmic expansion is now as well established as any law in astronomy, even though the ultimate cause of that expansion continues to puzzle theorists. The search for a deeper understanding of dark energy represents one of the most active areas of research in modern cosmology. Scientists are developing increasingly sophisticated instruments and techniques to study cosmic expansion with greater precision, hoping to detect subtle changes in dark energy's behavior that might provide clues to its fundamental nature. Future space missions will extend these observations even further, studying galaxies at earlier epochs in cosmic history, when dark energy was just beginning to dominate cosmic evolution. By mapping the expansion history of the universe with unprecedented detail, these missions may reveal whether dark energy has remained constant or evolved over cosmic time. Ground-based surveys are also contributing to this effort, cataloging the positions and redshifts of millions of galaxies to create the most detailed three-dimensional maps of cosmic structure ever attempted. These surveys reveal how matter has organized itself under the influence of both gravity and cosmic expansion, providing new insights into the interplay between these fundamental forces. The Dark Energy Spectroscopic Instrument, mounted on a telescope in the mountains of Arizona, can measure the distances to thousands of galaxies simultaneously, creating a vast database of cosmic expansion measurements. The preliminary results from this survey have already provided some of the most precise measurements of cosmic expansion ever obtained, while hinting at possible subtle variations in dark energy's behavior over cosmic time. These hints, if confirmed by future observations, could revolutionize our understanding of cosmic expansion and the nature of dark energy. They suggest that what astronomers have assumed to be a perfectly constant force might actually be slowly evolving as the universe ages. Such evolution could have profound implications for the ultimate fate of cosmic expansion and the long-term future of structure in the universe. So tonight, as we've journeyed together through this cosmic story, we've discovered that the universe expands around us with the same gentle patience that carries you towards sleep. We've seen how Edwin Hubble first noticed distant galaxies moving away, how scientists discovered the mysterious dark energy that drives acceleration, and how this expansion affects only the vastest scales while leaving your world unchanged. The space between galaxy clusters grows larger while you rest, but the atoms in your body, the distance to your ceiling, the orbit of Earth around the Sun, all remain perfectly stable. Whether you're awake or dreaming, whether you're thinking about these cosmic processes or simply breathing quietly in the dark, the universe continues its ancient work of expansion, creating infinite room for new stars, new worlds, and new possibilities to emerge across the endless reaches of space and time.